In tonight's session, we're going to look at how to solve substitution and elimination reactions when you're not necessarily given all the conditions or told which reaction is going to take place. For example, this right here, it could go one way, it could go another. In fact, let me know in the comments when you see a problem like this, what thought comes to mind for the reaction that'll take place. And typically, students like to do this with a flowchart, but I'm going to challenge you that in tonight's session, we are not going to use a flowchart. We'll come back to this reaction. Instead, we're going to use a very simple 4-part checklist that looks like this. Now, if you're not familiar with the checklist, I'll do a quick summary right now, but I have a full breakdown on it and I linked it in the description for this video. But the 4 things we're going to look for are partly to help us know what reaction can take place, but more importantly, to know which reactions we can rule out. For the alkyl chain, we're looking at the alpha and the beta carbon. The alpha carbon is the one that holds the leaving group. The beta carbon is the one next to it. And what we're looking at is, can we form a stable carbocation? Is it tertiary, meaning too hindered for an SN2 reaction? Can I form a pi bond? And I'll show you all of these in detail when we look at examples, but these are the questions to ask. For the attacker, it's less about looking at the difference between a nucleophile and a base and more about looking for a strong versus a weak attacker. Is my attacker neutral, or does he carry a burden of charge and wants to attack something? Will it go with a 1-type reaction, SN1 SN2, or a 2-type, SN1 E1, or a 2-type reaction, SN2 and E2. So that would be, strong would be a 2-type reaction and weak would be a 1-type. Then we're looking for the solvent. Is it polar protic or aprotic? Because if it is aprotic, this is going to help us consider an SN2 reaction over an E2. And finally, if we have a leaving group to consider, we want to ask, will it leave? Or will it turn right back around and not be gone, meaning if it's a bad leaving group, maybe the reaction can take place. So these are the things we're going to look at to help us figure out, without a flowchart, what reaction is going to happen. And let's apply this right here to the first problem. Now, for some of them, we can do a mechanism, but a lot of your professors will just give you a fill in the blank kind of question, or in the ACS, it's multiple choice. So I do want you to know how to come up with these without having to draw the mechanism. And for that, I'm going to show you some shortcuts as well, because I want you to be able to do this quickly. So let's break this down. And first, let me know in the comments, what do you think? SN1, SN2, E1, or E2 at first glance? And I'll put the reactions on the top so that we can rule them out together each time. Monique, absolutely. When we look at the SN2 reactions, I'll try to bring up an example, so please remind me. And I'm seeing a couple of different answers. Dehydration of the alcohol to an alkene via E1, yes. So first of all, I'm going to show you how to use the checklist, but in addition to that, I want you to recognize that H2SO4 and heat, when you're dealing with an alcohol, is most likely going to go for an E1 reaction. So starting with the alkyl chain, I'm looking at the alpha carbon. The alpha carbon is the carbon holding the leaving group, and in this case, the carbon can form a pretty good carbocation. That is because it is not only a secondary carbon, but it's also a secondary benzylic carbon. And if I form a carbocation here, that carbocation will resonate, be super stabilized, very happy. But at the same time, it doesn't help me rule out SN2 or E2. It doesn't help me rule out anything. I just know that a secondary carbon can form a carbocation. It can do everything. Secondary is useless. Between you and me, a secondary leaving group is nothing ruled out, which doesn't help you. So we'll move on. Beta carbon, we only have one right here. So if we had to form a pi bond, that would be the direction. The next thing we're looking at is the attacker, and this is where a lot of students get confused. What is the attacker in this situation? Remember, the attacker has to be a nucleophile or a base. And a nucleophile is something that is nucleophile, nucleus loving. And that means it's going to be something that is positive or partially, nucleus is positive or partially positive. The thing that attacks it is going to be negative or partially negative. And then a base is something that will attack or grab a hydrogen, a proton, and that means we're looking for something negative or partially negative. That is why I don't like for you to look at the difference between them. I want you to instead look at if it's strong or weak. Before we continue, if you want a copy of tonight's session notes as well as the bonus worksheet, go ahead and sign up on the URL on the screen or check the pinned comment, liveforsight.com/orgolive. As soon as I'm done, if you're watching the recording, you will also get an email as soon as you sign up for a link to tonight's session notes, everything that I draw today. You'll also get a bonus worksheet for additional practice and a link to the recording itself. All right, so we have, what do we have? The attacker in this case is not here. There is no attacker, or at least the attacker is not visible. We need something negative or partially negative, and all I have is H2SO4. H2SO4 is an acid catalyst. It's a source of protons in solution. Protons are positive, not negative or partially negative, but H2SO4 is not given by itself. H2SO4 is aqueous, and that means there is implied H2O, and H2O becomes the attacker. And that will help me figure out the difference. Is it strong or weak? The key here is that charge is a burden. And if I have an attacker with a negative charge, it is very reactive and it wants to do an SN2 or an E2 reaction. But water does not have a charge. Water is neutral. It's weak. It's not going to kick anything out. It's slow. It's going to wait. So the difference between an SN1 and an SN2 is in terms of the nucleophile attacking or waiting to attack. In an SN2 reaction, the nucleophile will come right in and attack, kicking out the leaving group. In an SN1 reaction, the nucleophile is weak and neutral and incapable of kicking something out. So it has to wait for that thing to leave. It has to wait for the carbocation to form. So we have just ruled out both the SN2 and E2 reaction because we have a weak attacker that is water. Next, we have the solvent. Is it polar protic or aprotic? And I saw a question about this earlier, so let's jump into it real quick. When we're looking at protic versus aprotic, what we have to remember is that they are both polar. It's polar protic or polar aprotic. Protic has the word proton in it, and that means we're looking for a solvent that can or cannot do proton donating, meaning a proton donor in hydrogen bonding. And the way I like to remember it is that hydrogen likes to have fun, F-O-N. If there's a hydrogen bound to fluorine, oxygen, or nitrogen, the electronegativity difference is going to be so strong that you're going to see a partial charge on the molecule. So for example, if I have water, oxygen is so partially negative and hydrogen so partially positive that if I bring another water molecule nearby, they are going to be very strongly attracted to each other because of those partial charges. This is a protic solvent. It has a proton available, a proton donor for hydrogen bonding because it's an oxygen or nitrogen, in this case an oxygen, bound to hydrogen. A polar protic solvent is very capable of stabilizing all kinds of charges, meaning a carbocation or anything similar that forms. And so it's going to support the one type reaction, the SN1 or the E1. Finally, we have to look at the leaving group. The leaving group in this case is OH. OH is a bad leaving group and it will not leave. So we have a problem. Everything else would work out if only the leaving group would leave. So how do we get it to go? Very simple. If it doesn't want to leave on its own, we bribe it. And how do we bribe it? With an acid catalyst. That's where the H2SO4 comes in. The oxygen will grab a proton. Now you get an OH2 plus. It's positive. Now it becomes a good leaving group. And once it's a good leaving group, it breaks off, it leaves. You're left with a carbocation and the reaction can proceed. We're stuck now between SN1 and E1. Now, technically, in a solution of water, if a carbocation forms and I have an SN1 reaction, I form an alcohol. So there is really no reaction happening, meaning even if it does SN1, it'll just keep reforming the alcohol. So that is why there is no SN1 reaction, because we won't see anything. Additionally, heat will help stabilize the formation of a pi bond, because a pi bond is a lot more stable and it requires heat to have that high activation energy so that you can have a much, much lower, more stable product. And so in this case, as I already told you, we're going to go with an E1 reaction. And if you have to come up with a product without the mechanism, here's how you do it. First, you redraw the skeleton of the molecule you're looking at. And then for elimination, you find the alpha and beta carbon, you draw a pi bond between the alpha and beta carbon, and you don't include the leaving group. And that's it. That is the product for the E1 reaction when using H2SO4 in a concentrated solution. If you have any questions on this, go ahead and type it in. We are specifically looking at substitution elimination reactions today, so anything else that you're asking about, ask me afterwards or email me, but we're going to focus just on substitution elimination. So let's try another example. All right, let's go down here. And this time, let's look at something like this. Professors love including rings on your exam. And so I want to make sure that if the ring scares you, you get that fear out of the way now. And the trick is just ignore the ring. Look at the rest of the molecule and treat it as a very, very simple problem. For this problem, you're given a molecule that looks scary, but hopefully is not. And you're asked to react it with NaOCH3 in the presence of CH3OH and heat. Your mission, should you choose to accept it, any Mission Impossible fans here, let me know. Your mission, should you choose to accept it, is to figure out if this is an SN1, SN2, E1, or E2 reaction and draw the major product only. So if your professor asks for just one, you could draw all of the different products, or I'll show you a shortcut that will help you find just the major product. So let me know in the comments if you consider this one easy, medium, or tricky, and if you want to learn my shortcut. But first, we have a question. Why was the previous one not a substitution, but an elimination? So let me show you something. If I have this molecule and I try to go, let me show you part of the mechanism. I think that will help. So I got to the point where I had my OH and it was protonated like that. So now I have a good leaving group, and as a good leaving group does, it leaves, giving me my carbocation intermediate that looks like this, with a carbocation sitting right over here, right? This is the part where we already understand. And the question from here is, what happens if I try to do a substitution reaction? To do an SN1 reaction, I'm going to find my nucleophile in solution, which in this case is water. A water molecule will attack. And when the water molecule attacks, well, isn't it just that right there? Water attached as an oxygen, 2 hydrogens, and a positive charge. And then if I deprotonate it, I get back to the alcohol. So when you're trying to show an SN1 of an alcohol reacting in water, your product is your reactant, and therefore technically there is no reaction. And so if some of the molecules will do SN1 and reform just the alcohol, eventually, according to Le Chatelier's principle, the more we pull out of solution, meaning the more product we form, the more is going to react. All the alcohols will eventually turn into alkenes until you have everything going in the direction of E1. That was a really good question, Monique. Let me know if that makes sense. And for the next one, I'm seeing both the correct answer and the fact that it's tricky. So let's take it one step at a time. We start with the alkyl chain. We notice that the alpha carbon is secondary, and I already told you secondary is useless. Secondary doesn't let us rule out anything. Let's also take a look at our alpha carbons. I'll mark this one in orange and this one in light green. Sorry, those are not 3 alpha carbons. What am I thinking? They're beta carbons because it's the carbon next to the alpha. Okay, so the alkyl chain, it just told us that the reaction can take place. Okay, not much help. Let's move on over to the attacker. What is the attacker in this situation? So I'm looking for what specifically the attacker is. And is the attacker strong or weak? Meaning, is it neutral or does it carry a burden of charge? Now, this molecule here is pretending to be neutral because it says NaOCH3, but the Na plus is a positive spectator. Don't let that trick you. Instead, identify that you have a CH3O minus, a negative charge. That is a strong attacker. This will give me a 2-type reaction. The moment that you recognize RO minus, rule out SN1 and rule out E1. There is no way we're forming a carbocation with a CH3O minus. Next, we move on to the solvent. The solvent in this case is polar protic. How do I know that it's polar protic? Protic, proton, I have a hydrogen on oxygen in the alcohol. An alcohol, a water, amine, those are all polar protic and will either favor SN2 over E2, or if I have a 1-type reaction, they will help stabilize a carbocation. Did I say SN2 over E2? I meant E2 over SN2. Polar, E2 over SN2. And in this case, because we're dealing with a 2-type reaction, a polar protic solvent tells me it will be E2 more than an SN2. And when you have heat, the same thing. E2 is favored over SN2 because the heat will provide a very high activation energy to give us a very stable E2 product. 2 things point to E2. Now we just look at the leaving group and verify that it is, in fact, a good leaving group and can leave. And based on that, let me just put this here for later. Based on that, I know that my reaction can take place. But the question is, how many products can I get? Let me know in the comments, how many E2 products can I get from this starting molecule? Meanwhile, we have a question. Why is E2 favored over SN2 for a polar protic solvent? If you have a good nucleophile, one way to recognize something that will act as a nucleophile rather than a base is the ability for it to polarize the charge, to concentrate all of the negativity in one corner. But if you have a polar protic solvent, now you're surrounding that nucleophile with partial charge. That charge now distributes to match the solvent. And so let me see if I could just draw it here. If I have something like, whoops, I'm not sure what just happened there. I was trying to draw on the bottom of this one here. If I have a good nucleophile, for example, an azide, N, triple N, single N, this right here, let me see. Yeah, this right here will have a -2 and a +1 for a net charge of -1. But notice how the charge is all concentrated. If this is in a polar aprotic solvent, it will happen like this so that it can, for example, attack a molecule that is very partially positive here. But if I then stick this thing into a molecule, into a solvent like water, and now I surround it with partially positive hydrogens over here and a partially negative oxygen over there and over there. Now the negativity is going to be drawn this way. Instead of taking all of the electron power and attacking, it's going to resonate this way and it's no longer as nucleophilic, where a base just wants to grab hydrogen and it'll happily grab a hydrogen off the water until eventually it grabs a hydrogen off the molecule. That is why a nucleophile is not as nucleophilic in a polar protic solvent, but a base is. So let's go back to this reaction. And I see a lot of 2s. The answer is actually 3. I can form a total of 3 products for this reaction. And let me show you. So the first, and the shortcut for this, if you don't want to draw the mechanism, is to identify your alpha carbon, identify your beta, draw a pi bond between them. We already said that trick before, so let's do that right now. We'll have our skeleton and then a pi bond between the alpha and beta. Let's do the same thing again. We have our skeleton and then a pi bond between the alpha and beta. I assume for everyone who said 2, this is what you were thinking. But here is one more product that you have to remember. If you have potential for cis and trans, trans is another product. You cannot forget your trans alkene. These are your 3 products for an E2, which is all very nice, but we weren't asked for 3 products, and that would be a waste of time. We're asked for the major product only. So you have 2 ways that you can come up with a major product. Option number 1 is do what I did here and then analyze everything. Recognize that this pi bond is the least substituted. That means it's the least stable. And if it's the least stable, this is going to be the minor product. Recognize that these 2 are the most substituted, therefore the most stable. But trans is more stable than cis, because with a cis product, these groups are very close to each other. They're sterically hindered. They're in each other's faces. And so trans is going to be the major product and cis would be the medium product. So these are the 3 products, but that wasn't the question. But first, thought there's one on the green beta carbon. I'm not sure I understand what you're asking. Each of the betas that I marked have hydrogens. The green has 3 hydrogens. The orange has 2 hydrogens. But the products would be the same regardless of which one we pick off. The only difference is if I rotate the molecule. And so if I'm looking at these 3, I can easily identify that this one is the most stable. It's the most substituted. And that makes it the Zaitsev product. But again, that's not what we were asked. If you are asked for the major product and you only want to find the major product, here is the trick. Identify your starting molecule. It's looking very crowded, so I'm going to remove the hydrogens. Look at the starting molecule, and then look at the substitution of your beta carbons. In this case, my beta carbons are as follows. The green one, whoops, why does it keep doing that? I don't know what just happened. Let's try that again. My green one is primary. The orange one is secondary. If you eliminate a hydrogen from a more substituted carbon, the resulting pi bond will be more substituted. And so the shortcut is to grab your skeleton and only draw a pi bond between alpha and the more substituted beta, where if you have a choice between cis and trans, only draw trans. And that is how you get your single major product, which looks like that. Major only, because this right here was the alpha, and this right here was my beta secondary. If you found this trick helpful and you think it's going to save you time on your exam, I want to see some hearts coming into the comments. Let me know that this was helpful. And let's take a couple of questions before we continue. I'm seeing the hearts coming in. Did I miss a lot? Yes and no. You don't have to worry about anything that you missed. Just go to liveforsci.com/orgo live. You'll get a link to the recording, all the notes from everything I'm drawing today, and the bonus worksheet for you to practice additional reactions so that you can really make sure you get this. So whatever you missed, you'll catch it right through that link. Question: if the BR were on a wedge or a dash, would it only form one of the cis-trans isomers? That is a very, very good question. So let's take a look. Ignore that. I'm just going to keep it there for when we need it next, but let's take a look at your question. If I have this molecule and I have, where did I have a bromine? Right there. And the bromine in this case is like that. If there were other molecules, if there were other substituents on the molecule, that would make a big difference because you want your hydrogen and your leaving group. So hydrogen and the leaving group must be anti. They have to be opposite each other and lined up in order for that E2 domino reaction to happen, which in the case of what we have here, it didn't matter because I have a hydrogen going into the plane of the page and another hydrogen coming out. However, if I draw them in different colors, in order for them to be anti, it has to be the orange hydrogen because I have to grab in a plane. So if I were to line them up perfectly, let's do a simpler version of this molecule. Let's say I have something like this with a bromine here and a hydrogen here, and then the molecule chain continues like that. We'll just call that R, and we'll just call that R as well. The base comes in, and what happens is the orbitals will collapse into each other as the electrons fall. So the hydrogen is grabbed, the electrons from hydrogen collapse this way, and that kicks out bromine like that. So it's like dominoes where they have to hit each other exactly in a straight line for them to get kicked out. And so if you were asked which hydrogen, it has to be the orange one, not the blue one. So in this case, it doesn't matter because they're both hydrogen. But if you had another group on here, let's say, this is a really good question. So that's why I'm taking a detour with this explanation. If anyone else was wondering about it and this detour is, you're finding this helpful, why did it go there? Let me know in the comments. But I'm going to draw out something like this. So professors like to do something crazy where they'll give you a molecule and then instead of a hydrogen, let's put something ridiculous like, let's put a tert-butyl group, something really big and bulky. Now, we want to make a trans product, but we absolutely cannot. The first thing that has to happen is you have to line up your hydrogen and your bromine so that you should be able to kick it out in a straight line. And the way that you do that, I'm going to have to redraw it because there's too much manipulation. The way that you do that is first start with what is not going to move. And that would be this right here with the tert-butyl group and the hydrogen coming forward. Now, in order to eliminate the bromine, I need the bromine to go dashes down. So that means I need to have a bromine here. What did I have to do? No, that doesn't make any sense. Hang on. Yeah, okay. So let's put that hydrogen there as well. Let me draw it exactly as you see it. This is where you can do either mental manipulation, and that's supposed to be a bromine, mental manipulation, or you can just say everything moves over one spot, and then you don't have to visualize it in your head. You just move everything one spot. The bromine moved from here to here, dashes down. The hydrogen moved up in the plane of the page like that, and then the methyl group moved that spot over there. So now I have the CH3 right there. Let me know in the comments if you followed me on the rotation. It's not drawn perfectly the way I have it here, but as long as they're anti, hydrogen is up and out of the page, bromine is down and into the page, they are anti-coplanar. I bring in my base, and then it probably will look better if I show it like this. Grab, down, down. Just imagine, you can kind of imagine that it's going in a straight line. And in this case, if you look at what you have for your final product, notice that the methyl group and the cyclohexane are actually facing each other. So when I draw it with my pi bond, I have the CH3 going down, and then the tert-butyl group is up there, which it would actually look a lot scarier. Let me move this here so you could see the whole product, but I'll change the color of the tert-butyl so you can see what I did. Up and like that, and there's my pi bond. Okay, not quite where we were going with it, because obviously this is not cis or trans, but instead I'm focusing on the fact that the molecule had to rotate in order to give me the kind of elimination that will be anti-periplanar. Okay, Eleonora, I hope I said your name right. Let me know if that makes sense. Aliyah, I covered that before, so you'll watch the recording. Question, does a back attack occur for substitution and elimination? I also need to understand the RNS configuration. Okay, so let's talk about the back attack, because that will bring us into our next problem. Say I have a molecule that looks like this, and I'm asked to react it with NaOH, just like we had before, but this time in DMSO. Looking at this reaction, what do you think? Is it going to follow SN1, SN2, E1, or E2? Also, let me know in the comments if you think this question is easy, medium, or hard. And let's see. We start with the alkyl chain. Again, secondary tells us absolutely nothing, but I needed it to be chiral, so it gave you a secondary molecule. Next, we look at the attacker. Is it strong or weak? Is it a nucleophile or a base? And in this case, I have Na plus, OH minus. It is a strong attacker. That means it's going to follow a two-type reaction. We rule out SN1, we rule out E1. Next, we look at the solvent. The solvent is DMSO. DMSO is one of the polar aprotic solvents that you need to memorize. It's polar aprotic, and that means it's going to favor SN2 over E2. Actually, before I continue, there was one more thing I wanted to mention here. We got carried away. Heat will just, oh no, we did talk about it, right? That heat will help stabilize the pi bond. Never mind that. Let's jump back to here. A polar aprotic solvent will favor SN2 over E2. And then we just make sure that the leaving group is a good enough leaving group so that it will leave and allow a reaction to happen. Chlorine will make a chloride halogen in solution. That's pretty good. No complaints. And so we have OH minus attacking from the back. Because OH minus is doing a direct attack, meaning it's not waiting for a carbocation to form, it wants to come in and attack. It can't come in where the chlorine is sticking out because chlorine is in the way, and so it has to come from the opposite side. The way to draw the product for this, even without a mechanism, is very simple. You redraw your skeleton exactly as you see it. Then, if your leaving group was on a wedge, you just draw dashes and you add in your nucleophile, in this case the OH, and that's your SN2 product, which I correctly saw Jeremy, Aditi, Chanti, I'm sorry, I can't pronounce your name. You are all absolutely correct. That is an SN2 reaction, and that's our final product. So I think that was Monique's question. Let me know if that helped. All right, let's see. Sometimes your professors will make it even harder. And so Morgan said easy. I like that. That should have been an easy problem. Let's try something very, very similar, where in this case we have iodine sitting on a 4-carbon chain reacting with the same situation, well, almost the same situation, NaOH. And that is all you're given. Easy, medium, or hard, and do you think it'll go SN1, SN2, E1, or E2? Here's the problem. The checklist requires us to look at a whole bunch of things, but we don't have a whole bunch of things to look at. So what do? Let's see. I start with the alkyl chain. My alpha carbon is primary. I cannot form a carbocation, so I have to rule out SN1 and E1. Then I look at my attacker. An Na plus positive spectator with an OH minus is a strong attacker. That means it will have to be a 2-type reaction, SN2 or E2. And typically I look at my solvent to differentiate between them, but we have no solvent given. And sometimes professors will do that on purpose. Okay, let's hold that thought. The leaving group is iodine. It's a good leaving group. So we know the reaction will take place, but the question is it SN2 or E2? If you don't have a solvent given, here is the trick to recognize. If no solvent, and you could have competition between SN2 and E2, the question is, which is faster? And why? That's what you have to ask between SN2 and E2. If all conditions, solvent aside, can lead to SN2 or E2, which one would be faster if I have a primary leaving group? And the answer is the SN1 reaction. The reason for that, the base or the nucleophile can come in, and to attack at the primary position, there is the least amount of steric hindrance. That means the primary carbon is going to be your easiest to attack, and the reaction that attacks the primary carbon is an SN2 reaction. So if your professor does this on the exam to trick you, I want you to recognize that it is an SN2, and absolutely correct. I saw a bunch of answers coming in. If I change this up, and this time I give you the same situation, but I put iodine on a secondary carbon. Once again, we're reacting it with NaOH, no solvent given. The question is SN2 or E2? And my question to you then is, which is faster and why? Is it going to be easier to do an E2 reaction or an SN2 reaction if the leaving group is on a secondary carbon? In this case, it will be an E2 reaction because the hydrogen is easier to reach. If it's internal, there's less steric hindrance. There's less blocking if we need to pluck off a hydrogen off of the beta carbon rather than a nucleophile having to come in and attack at the alpha carbon. And so in this case, the product is going to be a pi bond, Zaitsev's rule, more substituted. Oh, and for this one, I didn't show that to you. That will be just swap it out, and we put an OH right here. So absolutely correct. I see a couple of E2s. Awesome. I want to show you a few more where the checklist can backfire. And so it's not so much that the checklist can backfire, it's more about making sure that you're paying attention, because I don't want you to just memorize and assume it's going to happen a certain way. I want you to recognize what is going on. So this reaction, you'll probably recognize it from the last video, but I'm going to include it again. If I have a CH3Br and I react it with, let's go with NaOET in ETOH and heat, here's the checklist. What do you think? Easy, medium, or hard? And what is your first instinct? SN1, SN2, E1, or E2? And I want you to carefully think about what it is that we're looking at. All right, Morgan, I'm not sure if you're asking me, but you can go here. All right, so the alkyl chain, actually, let's do this backwards because I want to show you where students get tripped up. We have a good leaving group. That means the reaction can take place. The solvent is polar protic. That means if we have a two-type reaction, we're going to favor the E2 over SN2 for a polar protic solvent. My attacker is strong. That means it's going to be a two-type reaction. Rule out SN1 and E1. And typically when students see a base and a conjugate solvent, they immediately think E2 reaction. And it would favor an E2 reaction. But the problem is if you look at the alkyl chain, we cannot form an E2 reaction here because we have to look at two things with the alkyl chain. We look at the alpha carbon, and the alpha carbon is a methyl group. A methyl group tells me no carbocation, so that would have helped me rule out the SN1 and E1. But the other thing I look at is the beta carbon. And in this case, I have no beta carbon. That means I can pluck off no beta hydrogen, no pi bond. And if I can't form a pi bond, I can't do an elimination reaction. And that means this is going to be an unexpected SN2 reaction. The trick for the SN2 again is you redraw your carbon skeleton. In this case, it's just a carbon. Then we add whatever you have here as your nucleophile attached to it. So OET, and that's the product. Question, can you explain the concept of anti-coplanar geometry in E2 reaction? How does it influence the reaction mechanism and product formation? Aaliyah, I'm not sure if you're asking for the definition or the concept. So let's go back to this. The idea with anti-coplanar is you want all of the electrons to be lined up and so that the orbitals can collapse into each other. When the base grabs the hydrogen, the orbital of the electrons, and this is beyond what you need to understand in organic chemistry. I just want you to think of it as dominoes. It has to be able to grab and everything collapse in a straight line. And in terms of how it influences the reaction mechanism, if you have a situation where it's not lined up to be in a straight line, so I showed you the hydrogen forward here and the bromine forward, you have to rotate it before the mechanism can happen so that everything gets eliminated in a straight line. Here, it doesn't look very straight because hydrogen is coming forward and bromine is going back, but the idea is that one is coming out of the page, one is going into the page. They are perfectly lined up. If you do this in a Newman projection, that is going to be another way to recognize it. And in fact, let's do another problem based on that concept. So that's a really good question. Say I have a molecule that looks like this with a chlorine coming out of the page, and I have a CH3 coming out of the page here, an ethyl group coming out of the page here. So that's my starting molecule. I want to react it with NaOCH3 and CH3OH and heat. The first thing we have to figure out is what reaction is going to take place here. Will it be SN1, SN2, E1, or E2? Let me know in the comments if you think this is easy, medium, or hard, and we'll work through it together. And a question on the previous one, which connects here. If the H is on the wedge and the bromine is on the dash, that's considered anticoplanar? Yes, because you want them lining up in the same plane, but anti to each other, one up and one down. Question while you're typing your choices in. On the ACS exam, are you solely responsible for recognizing SN1, SN2, E1, E2, and predicting the product? No, you are responsible for everything. Even though you don't have to draw a mechanism, the ACS will sometimes ask for in-between questions, meaning what does the intermediate look like, or which one will have the least stable intermediate, or what are the steps of the reaction, and they will list it out, step 1, 2, 3, in the multiple choice, meaning say there are 3 steps, they may give you choice A, 1, 2, 3, choice B, 1, 2, 3, 4, choice C, 1, 2. So you have to know everything to be able to pick and choose the right answer. All right, so looking back at this, let's go down the list real quick. Alkyl chain, we have the leaving group sitting right here on a secondary carbon doesn't tell me anything. I also need to look at the beta, and I'll draw in the beta hydrogens. I have a green beta hydrogen going down on the methyl position. I have a blue beta hydrogen coming up on the ethyl position. Both of them can form a pi bond, and both will give me the same level of substitution, meaning stability would technically be the same. The attacker, Na plus positive spectator, CH3O minus is a strong negative attacker, rule out SN1 and E1. Solvent is polar protic. That means we will favor an E2 over an SN2 reaction. And the leaving group is a good leaving group, so it's not going to give me any trouble. I will have an E2 reaction take place. The question is my E2 product going to be the one where I have a pi bond at the green carbon, right there? Not the green carbon, the green hydrogen. And then I have an ethyl group remaining here. Or is my product going to be eliminating the blue hydrogen, and so the methyl remains here, and that's my ethyl. Notice that according to Zaitsev's rule, they both qualify. They are the same level of substitution. And no, we're not going to get both, only one. What do you think? Which one is it? And more importantly, why? If you're not sure, let's see the concept of anti-periplanar on a chair conformation. Because if you can't see it this way, a chair conformation is going to make it very clear. So we'll draw a chair this way. The first thing is on a chair conformation, for an E2 chair, your leaving group and your hydrogen must be axial. And so I will start by putting the chlorine up here. Notice it's on a wedge. I put it in the up position, and I'll just count my way clockwise. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm only going to fill in what matters. Ethyl is down on 2 with the hydrogen up on 2. Up is equatorial, down is axial. On carbon 6, I have a methyl up. That is equatorial. And on carbon 6, I have a hydrogen down. That is axial. Which one is perfectly lined up with the chlorine, meaning one is up, one is down, and I can eliminate in a straight line? It's the green one. If the base comes in, grabs the hydrogen, collapse, collapse. Whoops, that's supposed to be an arrow. Instead, it looks drunk. This right here is following a very straight path. The electrons are perfectly falling into each other, eliminating in anti-periplanar. And hopefully you can see this very clearly on a chair conformation, which is going to give us a second rule. They must be axial, but they must also be trans and axial. Do you see that? Hydrogen and chlorine are trans. Therefore, if they're trans and they're axial, meaning not equatorial, that will give me the product. And so this right here is my product, not this one. But what if you don't want to take the time to draw out a chair conformation on your exam because you don't have time on your ACS, or you're stressed, or just you don't want to waste that kind of time and you want a shortcut? Let me see some hearts in the comments if you want to see a shortcut that will never have you drawing a chair again for E2 reactions. Also, if you haven't subscribed to my channel yet, you're almost an hour into this live stream. Go ahead and hit that subscribe button because, come on, what are you waiting for? Also, I'm trying to hit 1 million subscribers in the next 5 years, so I do need your help. Go ahead and subscribe just for that, if nothing else, and tell your friends. All right, I'm seeing the hearts, so let's take a look. What if, instead of having to draw it out and seeing transaxial, I just look at this and say trans? What does it mean for them to be trans? They have to be opposite each other. Notice that chlorine and hydrogen are cis. Cis to chlorine, no good. Notice that this one here is trans to chlorine. So the shortcut, if this is what you're given, is very simple. Find the hydrogen that is trans to your leaving group, and that is how you eliminate. So redraw the skeleton. Don't put your leaving group, obviously that disappears. Draw the pi bond in the direction of where the hydrogen was trans. Put everything else onto the molecule. Also notice that I put the CH3 on a line rather than a wedge, and that's because the hybridization here is, well, not here, here is sp3. sp3 is three-dimensional, it's trigonal planar. But if I look at the hybridization here with a pi bond, that is sp2. I'm sorry, sp3 is a tetrahedron. Clearly tired. sp2 is trigonal planar. That is flat, and that's why we have no more dash or wedge. It's sitting on a straight line. Jeremy says, dang, didn't even think of that. So Jeremy, let me know if you just saved at least 30 to 90 seconds on your exam. So let's try another one just to make sure that you're comfortable with it. Once again, we'll start with a cyclohexane. And this time we'll have an iodine sitting up here. And then over here we'll have, I don't know why I put that in a different color, we'll have a CH3. And that is the only substituent. Now, if we're looking at this molecule, it makes the most sense that the alpha and substituted beta is the perfect place to get a pi bond because that will follow Zaitsev's rule. Give me the most substituted pi bond. The problem is, look at the hydrogen. The hydrogen that is sitting on this beta carbon is cis to the leaving group, not trans. And that means even though it would give me the more substituted, more stable pi bond, I have no way of grabbing it. I have no way of getting that off because it's not anti. And so I have to find another nearby carbon that has a hydrogen going back down into the page. I didn't even give you reagents for this because I was going for E2, but let's fill it in. Let's go with NaOH, H2O, and heat. And just to show you on the checklist why it works, we have the alkyl chain. Doesn't tell me much for the alpha. The beta just helped me figure out where to go. The attacker is Na plus positive spectator. OH minus is strong. Rule out SN1 and E1. My solvent is polar protic. That means E2 is favored over SN2. And then heat also favors E2 over SN2, and I have a good leaving group. So that is how we know it's an E2 reaction, which I kind of just took for granted in setting up this problem. And then we draw our skeleton. We know we're not touching that methyl group, so the stereochemistry does not change. Have a CH3 right there. We eliminate the leaving group and the hydrogen and put a pi bond between those two positions, and we get an unexpected, less substituted pi bond because, very simple, the leaving group and hydrogen must be anti. And this is on a chair. Or, yeah, it's on a chair, even though we didn't draw it on a chair. This is your shortcut to save you time on the exam. Okay, I'm seeing questions for other things, which we're not going to focus on. We're just going to focus on substitution and elimination today. What do you think? One more? And if yes, as I draw the problem on the screen, let me know in the chat, or if you're watching the recording, let me know in the comments, which tip that we covered today did you find most helpful that's going to save you the most time on your upcoming final exam? I'm thinking, trying to think of a good one for the last one. We'll keep it simple, but we'll make it good. And the question is SN1, SN2, E1, E2, and how did you know? Well, let's go through the checklist. First, the alkyl chain. Actually, let's go through the checklist backwards. We'll start with the leaving group. Chlorine is a good leaving group, and so doesn't tell us anything except that the reaction can happen. Next, we're looking at the solvent, or would be looking at the solvent. But what's the solvent? What are we looking at here? Anytime you have acid with nothing else given, assume that it's taking place in water. Your solvent is implied. And the solvent is polar protic. If we have a two-type reaction, we know that E2 is favored over SN2, but we haven't yet ruled out anything, so we don't know. Next, we look at the attacker. And the question is, what's the attacker? Because I didn't give you that either. All I gave you was H2SO4, which is the source of protons in solution. Remember we said earlier, the attacker has to be negative or partially negative. And so if you don't have an attacker, just an acid catalyst, this is a Solvolysis reaction. Solvolysis has the words salvo, the solvent, lysis, breaks. The solvent is your attacker. Water is neutral. Water is weak. Water will not allow an SN2 or E2 reaction because it's not strong enough to kick anything out. It has to wait for a carbocation. And that leaves me with the alkyl chain. Now the alpha carbon, well, let's start with a beta carbon. The only beta carbon is here, and it has no beta hydrogen. If I have no beta hydrogen, I cannot form a pi bond, and that means I cannot have an elimination reaction. So E1 is ruled out. The only reaction left is SN1. But look at the alpha carbon. My alpha is primary. Can I form a carbocation on a primary leaving group? Technically, no, but it's not primary by itself. It's a primary benzylic, and the benzylic group can have resonance, can stabilize, and that is going to allow the primary carbocation to form. That is going to then allow my SN1 reaction. The trick for drawing the product of an SN1 reaction without the mechanism is to redraw the skeleton exactly as you see it. And then in place of the leaving group, you put a bond to, take your molecule, you remove one hydrogen, and that's what you add. So if you have water, you remove the hydrogen, and you just add the OH. That is the shortcut for coming up with your SN1 product. For even more practice on substitution and elimination reactions, make sure to visit the link on the screen, layerforsci.com/orgolive, where you'll get a copy of tonight's session notes and a bonus worksheet for additional practice.